In this tutorial in modulation, we're going to look at frequency modulation. Now, as I said in the AM modulation one, I am firmly convinced that the best way of explaining or getting an understanding of modulation is to look at what's going on in a visual manner and use the maths to sort of support it. So what I've done here is I've created another Excel spreadsheet, and this one deals with frequency modulation. Once again, we've got the basic expression for a waveform up here, where we have the magnitude of the wave, the fact that it's a sine wave, the frequency of the wave, and we can display any phase shift of the sine wave. For the purposes of these, we're not going to have any phase shift at all. What I've got down here is a visual representation of an FM wave in the time domain, which will be changed as we add some of these values into it. Here is a mathematical expression for an FM waveform, and this here shows the frequency spread or the spectra of an FM wave. Now, I just want to make one quick observation here, and that's the way that I've done this Excel spreadsheet would appear to show these as being three distinct frequencies. It's not. This here really should be shown as a block, and perhaps I should go off and redraw my Excel spreadsheet to show this as being almost a solid block, where we're using all these frequencies in here as well, as we can see through here. But this is just done for some demonstration. I based this spreadsheet on the AM one, as you'll probably notice, and I haven't done that. Now, up here is a visual representation of the carrier wave and the modulating wave that we're going to be using our FM waveforms for. And up here is a mathematical representation of our sine waves and our modulation index. So let's get into it. The first thing about frequency modulation that you really need to understand is that, as the name implies, the frequency of the carrier wave is modulated. In AM modulation, it's the amplitude. In the frequency modulation, it's the frequency. Now that sounds pretty straightforward, but it has some really quite important and fundamental things that matter. One of these is the simple fact that FM is immune from noise. If we were to have a noise spike come in here, for example, it would make absolutely no difference because there's no encoding on the amplitude of this waveform. If this waveform gets to the other end and it is only a couple of volts high down here, as opposed to the 10 that I've got shown here, no data is lost or corrupted because there's no encoding on the amplitude of the waveform. Unlike an AM waveform, if we had some amplitude changes through noise or whatever, we can get some form of error. In an FM waveform, that simply doesn't happen because there's no encoding on the magnitude of the waveform. All the encoding is done in here with a change of frequency. Now, this is kind of quite cool. The other thing that's quite interesting is the magnitude of the modulating frequency has no effect. We can see in here in the mathematical expression that there is no term in here for the magnitude of the modulating wave. It's simply not there. Here's the magnitude of the carrier wave. In this particular example, it's written as a cosine. It doesn't really matter. We've got the frequency of the carrier, the frequency of the modulation wave here, and this term here, delta F or F delta. But nowhere in there is M. So if I change this to anything, if I change this to 100, it makes absolutely no difference to our resulting waveform. It makes no difference to it in the time domain or the frequency domain. If I put it down at 0.1, it makes absolutely no difference, and that's kind of cool. Now, the other thing that we need to understand here is the modulation index. In an AM waveform, the modulation index was a ratio between the magnitude of the two waveforms. In FM, the modulation is not a function of these two, but rather it's a function of the change in frequency here. And this is the relationship here. So we have a relationship between the frequency of the modulating wave, the modulation index, and this change of frequency. And that's a simple algebraic expression, and whichever way around you choose to manipulate that, it doesn't really matter. We can define what one will be, and that will calculate the other. For example, I could define what delta F would be, and then for a given modulating frequency we would end up with a given modulation index. This particular case here, I am defining the modulation index, which will calculate our delta F. Now, I can make, for example, if I made modulation index 1, that in this particular case, using these particular numbers, would mean that my change in frequency would be 1 down here as well. Now, the reason these are coming out the same is because of the relationship here. So if I was to make this, say, 3, here we are now, with a carrier wave of 3 Hz and modulation of index of 2, we get a frequency spectra of plus or minus 6. So here we are with our carrier at 10 Hz, here it is here, and a modulation index of 2 with a modulating frequency of 3. It gives us a plus or minus 6 Hz here. So we end up with from 4 to 16. So if we were to look at the expression down here, we see that the resulting FM wave, the magnitude of it is the magnitude of our carrier, here it is here, 10, and times the carrier wave plus delta F over FM, which is that, times the modulation frequency. And so this is what we see down here. We can see that as we change these values, we can see a change in the frequency of our carrier wave. For example, at 5 and 2, we can see here that for this part here, we end up with a lower frequency, and for this part here, we end up with a higher frequency in our waveform. So let's just play with some numbers and see if we can get something that really quite shows it quite well. Yeah. So this shows it quite extreme, how in this particular part of the cycle we have a very high frequency, and in this part of the cycle we have a very low frequency. So we can see how our frequency is modulated according to our modulating waveform here. When the modulating wave is got a high value, in this case plus 10, our carrier frequency is altered to be the lowest possible frequency. When it is down here and we have a amplitude of minus 10 on our modulating wave, our carrier wave is operating at its highest frequency. So our modulating wave here is encoded on a carrier signal, and the frequency of our carrier signal is adjusted accordingly. And this is our basic FM signal. Thanks for watching.